this month's 1 week earlier than originally planned Developers Forum. So thanks for everybody for joining. Today we have a nice presentation, hopefully from Jiefei Wang, who has a fantastic looking GitHub repository or GitHub account that's full of R packages doing lots of cool sounding, very techy projects. So covering things like GPU processing, sharing objects between different, in memory between different R processes and things. But today, hopefully he's going to talk about a package he's been working on called Travel, which is kind of going to be a direct follow-up to last month's ALTREP, where we kind of learned an introduction and some of the fundamentals behind it from Gabe. And then Jiefei is going to talk a little bit about some of the problems he's run into using it and a bit of sort of practical work with it, hopefully. So without further ado, Jiefei, please, the floor is yours.
Thanks for the introduction. So it's my pleasure to have a talk here, and I will start to share my screen. And can you guys see my slides now?
Yes, they're working now.
Okay, so I'm Jiefei Wang from Bioconductor, and today I will continue the talk in our previous presentation and discuss the idea of ALTREP. So my topic here today is say hello to ALTREP. And here's the outline for my talk. So first I will briefly go over the concept of the ALTREP. Then I will show some challenges with the ALTREP. And then after that, I will bring my travel package. So after introduce my travel package, I will show some travel examples. And first, let's talk about the concept of ALTREP. So before I talk about detail of ALTREP, so let's first say how R spectre looks like in the memory. So if we know the motivation of the ALTREP, we can have a better understanding of it. And here's how it looks like in memory. A vector in R is just a header plus its payload. And header it stores some information of the vector, like the type of the vector, length, and the attributes. And the payload stores all the values of the vectors. And on the right side is how it looks like in memory. So in the first few cells, the orange cells is a header data, and right behind it is the payload. And here's two major characteristics with R spectre. The header and the payload are not separable. And second, the payload must be the entire data of the vector. So in other words, it cannot be a compressed data. So, and that brings some room for the optimization. And so for the first point, let's say if we have a code like this, we create a vector x, and then we assign x to the variable y. So from us perspective, a variable is just the name of the internal memory object. So basically, after you do the assignment, your x and y will share the same memory object. And then at some point, maybe you change your mind. You say, okay, I don't want a vector, I want a matrix. And in R, a matrix is nothing but a vector with the dim attributes. So in order to change its attribute, you cannot directly find out the internal memory object and change its attribute, because Y also shares the same memory object. So you have to copy the entire memory object and then do the assignment after you copy it. So, and you see, here we clearly have some place for optimization, because the X and Y share the same payload. So and the payload is not going to be changed when we set the attributes. So ideally, we can just copy the header and let them share the same payload in the memory, so that we save the time of duplicating the payload. And for the second one, the payload must be the entire data of the vector. So like, for example, if you have a vector from a sequence from 1 to 100, and you know that's an arithmetic sequence, so that you don't have to store everything in the memory. You don't have to store its data in the memory. And as long as you know its starting value and the length, you can reconstruct its values in the vector. However, this is not possible with a regular vector. So it has such restrictions so that the header and the payload are celled together. And also your payload must be the entire data. So the first cell in your memory is the first element in the vector, and the second one is the second element, and so on. So that's the motivation for the ALTREP. We would like to design a feature such that the payload and the header and the payload are not tightly linked together. And also the data will allow an arbitrary data structure to represent the vector. So here's the ALTREP. So now we have an ALTREP vector. Like internally, it's a header plus its payload. And now this time, the header and the payload are separate, so that your header can locate in the memory in the first few cells, and your payload can be some other place. And so it brings two features, first, the header and the payload can be linked and unlinked at any time. And so that if you change the attribute of X, so you don't have to copy the entire data. You just copy the header and then link the header with your old payload. And the second, the payload can be anything, can be any data structure, as long as it can represent the data, as long as you can use it to reconstruct the data in the vector. So that sounds the idea of the ALTREP sounds promising and exciting, and ALTREP is designed with the hope that it does not break the existing user's code. So every time when you have a new feature, you want it to be compatible with the existing code as much as possible. So if it's not compatible, then it may bring more troubles than its benefit. So how ALTREP do it? And here's a program diagram for R. So users sit at the top of the diagram, and they can call some C or C++ code in R, and they can also call R code. And for the R code, it will go through a repo, which is responsible for evaluating your R code and translate it into the corresponding RC interface to do the job. And RC interface will be responsible for getting the data from the vector from the memory. So for example, if you want to access the S element in the vector X, suppose this X is a numeric vector. And then in the repo, it will realize that this is a numeric vector. So it will call real element function in RC interface to get the S element of X. And for RC interface, and if this X is a regular vector and it has data in memory, so it can just use the pointer for the vector X to access its data. So that's the that's how we evaluate our R code in the program. And as you may can guess, because we don't want to break the existing user's code, so ALTREP is designed is hidden behind the RC interface, and it is able to dispatch your accessor functions to other customized functions, so that when you access the values in the vector, and you want to directly use the pointer to get the data from the memory, and it may call some other functions to get the values, to give the value to you, so that you don't have to have the entire data allocated in memory to make the vector work. And here are a few popular accessor functions for the numeric vector, namely real element and get region and data pointer or real. And for these last two, the data pointer is a more generic version for getting the data pointer, and the real is specifically for numerical vector. But basically, they are the same thing. And so everything looks good. And here are some low-hanging fruit for the ALTREP. So first is the attributes wrapper. So as we mentioned before, like that's one motivation for the ALTREP. With the wrapper, we are able to change the attributes of a vector without duplicating its payload. And the compact sequence, that's also shown before, in the previous slides. So we are able to create a sequence, a very large sequence without using too much memory. And then the third, sharing data across multiple R processes. So because the payload does not have to be from memory, so does not have to be from your R process. So you could put the payload into the shared memory space, and each R process only has a header. And by doing so you can easily share a large object across many R workers without duplicating its payload into each process. And shared object is a package for doing this job. And also we have on-disk data representation. And this time the payload is not from memory, it's from an on-disk file. And room is a package for reading the text format data. So everything looks good until now. And here's the challenge with ALTREP. With great flexibility comes great complexity. So ALTREP is so flexible so that even though we hope that it won't break the existing code, but in practice, some RC code is compatible with ALTREP, but some are not. And this is true even for the base R. And the second point is that even though the code is compatible, but compatibility does not grant efficiency. So your code may not be very efficient, and it may not be fast. So I will show these two challenges with an example. Let's say we want to compute the sum of a vector. So here's my silly sum function in R, and it's pretty straightforward. First, I just allocate a variable for holding the result, and then I loop over the vector x, and I add the values of the x into the result, and then return the result. So it's simple and straightforward. And now let's go to the C level to see how we implement it at C level. And now for simplicity, we just assume the vector is a numeric vector. So for integer vector, there's another set of functions to access the element of the vector. And we have three most popular RC API to access the data of the vector. For the element function, here's the implementation, my silly sum function 1. So it's similar to the R function. First, we just declare a variable to hold the result, and then we loop over the vector using the real element function to get one element from vector x at each time, and then we add it to our variable s, and then we return our result. So it's simple and straightforward. And the second is get region function. So in practice, usually we do not use get region function because it's really hard to make it right, and you have to allocate a buffer for it. And so luckily, and R source provide a macro for us to iterate by region, which in turn it will call the get region function to read the data from X. And now this time the code is a little bit hard to read. I'm not going to explain what does this variable means in the macro, but the basic idea is to read the data into a buffer, and inside the macro you just need to loop over the buffer and the macro will help you to do the right thing. So the last implementation, the data pointer. So this is probably the most favorable implementation for a C programmer, because all you need to do is just get a data pointer from X, and because I know it's a numeric vector, so it's a double precision pointer, and then the rest is just pure C code, and you loop over a pointer and get its value, add it to your variable S, and return S. So we have 3 different RC APIs. We have 3 different implementation. So which one is the fast one? So here is my personal judgment for these 3 implementation using the GitHub stars. And for the first one, real element, and I think it has it's the slowest one among all these methods, because the real element is a function, and actually calling a function just for getting one element from X, that may not be that worthy. And for the get region one, and you still need to call get region to get the data from X, but this time you get a chunk of data from X, so it has a better performance. And for the data pointer, because working through a pointer in C is extremely fast, so this should be the performance beast. And now let's talk about the conciseness. So you can clearly see the size of the code by looking at the code block. And the first one and the third one is the most concise one. And the second one, even though it's not lengthy, but you still have few more lines to write. And the last one is probably another important factor for developers, so readability. And for the first implementation and the third is really straightforward, and you can easily understand. And for the second one, unless you are really familiar with the iterate by region macro, otherwise you have to stop here for a few seconds and understand what's the meaning of each variable. So it has the worst. It will be problematic for the maintainer. So now let's do some performance comparison. So let's say we have a randomly created numeric vector, and its type is numeric, and we can check its data. They are all random number, and we can get its size using object size function, and it's 1 GB. And we can use internal inspect function to check that it is not an ALTREP. All the data has been allocated in memory. So this is just the traditional R vector. And now for the element function, it takes about 2.5 seconds to finish the mySum function. For region function, it takes less than 1 second to finish. And for data pointer, it also takes less than 1 second. So this can confirm, at least can confirm my judgment of the performance. The first implementation has the worst performance, and the second one and third one, actually in this example, they should at the same level. And now, what if our vector is an ALTREP? Now, in this turn, I will create an ALTREP object in R. So I use the sequence function to create a numeric sequence, and you can check its type is numeric, and its value is just a numeric sequence from 1 to its length. And if you use object size, it will falsely give you it will falsely tell you that it is 16 GB, but actually this is the size that if you allocate the entire data in the memory. And if you use the inspect function, and you can see it's a compact sequence. And here's one interesting observation. It seems like the print format, there's some formatting issue with the inspect function. But anyway, so here we have the ALTREP, and it does not allocate its data in memory. So what's the performance in these three implementations? So first, element function, and it takes 42 seconds to finish. So I should say that this vector has a different length than the previous vector. So you cannot compare this number with the previous one. And get region function, it takes about 4 seconds to finish. So you can see a great performance improvement over the element function. And now for the data pointer. So what if you ask for a data pointer to the object which does not have a data pointer? So here you can see an arrow from the sum function. It says it cannot allocate vector of size 16 GB. So if you ask for the data pointer for an ALTREP object which do not have data in memory, then you force it to allocate the data for you. But actually, because of the hardware limitation, like it cannot allocate such huge object. So your function failed. And now this is a recap of what I have about the challenges with the ALTREP. Some RC code is compatible with ALTREP. Like this first two, you don't have to change anything to make it work with ALTREP. But some are not, like the third implementation, and you just cannot allocate that large memory. And also, compatibility does not mean efficiency. So even though the first and the second one works with ALTREP, and you can clearly see the performance difference between these two implementations. So that's the challenge with ALTREP. Before I bring my solution, so I would like to take another look for the problem. So I would like to say how frequent these three API are used in our package in the Bioconductor repository. So if no one uses these three functions, so which means the problem is minor, so we can just ignore it and pretend that it's not true. So for the first one, real element, and you get 0 result in 0 files. It seems like no one likes this function. And for the get region function, you get 5 results in 1 file. And actually, this file is from my shared object package. So because I use this macro because I know ALTREP, and I know some ALTREP do not have a pointer. So I want my function to be both efficient and compatible with ALTREP. And I'm the only people to give an upvote to this macro in Bioconductor community. And the third, data pointer, you get over 3,000 results in 500 files. So it seems like everyone likes the data pointer. It's simple, it's straightforward, and easy and understandable. And also, this is the editor's choice. And you can see data pointer everywhere in the R source. So now, how can we solve this problem? How can we make the ALTREP vector works with the data pointer function? Can we give a pointer to the data to an ALTREP vector without allocating the data in memory? So that brings the travel package. Travel is a package for creating a virtual pointer that the ALTREP object needs. So it's a tool for the developer, not for the user, to create the ALTREP object. And how can we make that possible? So now let's go back to the program diagram. And so it's the same diagram now. And we are told that the C and the C++ code are a kind of low-level code. And it is close to your hardware. So, and the pointer is clearly one of the core concepts for C language. And it actually stores the address of the data in memory. And if you have a pointer, and of course I did not assign the value to the pointer, but let's pretend that this pointer points to some useful data. And we evaluate it, we get value from the pointer. So we think that it will go to the memory, find out the right location, and get the value for us. So that's the concept of the pointer. So if with that concept in mind, how can we give a pointer to C code which behave exactly the same as a pointer, but actually it's not but actually with no data in memory? So that job seems impossible with this diagram, but luckily we have him, David Wheeler. He said all problems in computer science can be solved by another level of indirection. So which means if a problem is too hard to solve, adding one more layers may be helpful and may be able to make the problem solvable. So if this diagram is not enough for our job, we bring this one. We bring the operating system into our game. Actually, we saw that the pointer is the address in the memory, but in reality, this is not true. So actually, your pointer interacts with the operating system, and it is the operating system's job to get the data from the memory. So that if we have a way to let the operating system, like to hijack the operating system's data access request from the memory to some user-defined function, so we are able to make a pointer which behaves exactly as a normal pointer, but actually when you access its data, it's called a user-defined function to get data for you. So you may can have a guess on where the travel package is. So it is a plugin for the operating system, and it is able to make a pointer so that the operating system will dispatch the data access request to the user-defined function. Let's assume that X is a travel-made pointer, and then if you ask for the data from the pointer, then conceptually the operating system can call get element function to get the data for the X. So that's the concept of the travel package. And now let's look at the there's one more thing. So this all the things inside this box are the R program, and what travel does is invisible to the R program. So your good old existing code can happily work without worrying how the pointer is actually treated on the line. And then let's look at the API in travel package. So this is a C++ function in the travel package, and developer can call this function to create an ALTREP object. The input is the ALTREP info to tell the travel how you would like the ALTREP be, and the return value is just an ALTREP. And here's the data structure for the ALTREP info. You define this is the operations for the ALTREP, which defines the behavior of the ALTREP and the type of the ALTREP, like the integer or numeric, and the length of the ALTREP. And I'm not going to cover these two members. And so on the right panel is all the operation available for the travel package. So don't be scared by this struct. And for the simplest ALTREP vector, all you need to do is to define the get region function and the type and the length, and then the vector will work. So you are safe to ignore the rest. So let's see an example. So here is an example to make our homebrew version of the compact sequence. And here's the constructor function, travel compact sequence. And first, you need to declare your ALTREP info and assign its length and set its type. Here, I just set it to numeric vector. And then define its get region function. And in this get region function, it has 4 parameters. The first one is ALTREP info you just declared. And second is the buffer that is going to hold the data, hold the region data. And the third one is the element offset of the vector. And the last one is the length of the element that's going to be read to the buffer. And in the function body, I just loop over the buffer using double pointer. So because I know that this is a numeric vector. So in the memory, it's just a double precision value. And I loop over the buffer and assign it the offset +1, because we know like C is 0-based offset and R is 1-based. And then at the last line, I return the length that I read into the buffer. So here's all you need to do to create an ALTREP from the travel package. And also the ALTREP returned by the travel package has a pointer available. Okay, yeah, the last line is just called travel make ALTREP, and with your ALTREP info to make an ALTREP, and you can return the X. So now let's go back to our performance comparison. Now we have 2 candidates. One is the naive R compact sequence, and one is our homebrew travel compact sequence. And from our perspective, there's no difference between X and Y. And you can see the type is numeric. The data is exactly the same. And also, the false report is also exactly the same. And you can only tell the difference by using the inspect function. And one is a compact sequence, and the other is travel ALTREP. Now we have 2 candidates. We can use our 3 different implementation of the sum function to compare its performance. So the first one is the element function. So you can see the number for the travel-made compact sequence is off the chart. And actually, the reason is twofold. First is because if the element function see that a vector has a pointer, then it will call the data pointer to get the data from the vector. And getting the data getting the data pointer for a travel package, for a travel-made ALTREP, is not a trivial job. So that contributes to part of this time. And the second reason is that the travel package is still under development. So some functions in the package are lack of optimization. And luckily, we know that the real element is not people do not use it in Bioconductor community. So this gave me the chance to do the optimization. And after I implement the optimization, and we can expect that these 2 numbers are in the same magnitude. So the second one is the get region function, and they have the fairly equal performance. So this is not quite surprising. Excuse me. This is not quite surprising, like they use the get region to read the data. And the third one, which is the problematic one for the naive compact sequence, because it cannot allocate the data. And now this time, with the travel's help, we can return a virtual pointer to the MySum3 function, and then it can happily loop over the pointer and compute the sum of the vector y. And so by using the travel package, not only it solves the compatibility problem, you can see it also brings some performance benefits. And this number is the smallest number among all the numbers in the chart. So the travel package can solve compatibility and also give you some performance boost. And then I would like to show an application for the travel package, the Highfive package, which is a package to read HDF5 files into as an ALTREP. So here's a simple example files I prepared. So this H5 file has two objects, and one is object A, and it's an integer matrix, and the other is a data frame df, and it's a compound type in the H5 file, and this is the number of rows the data frame has. So first, let's read the matrix A. And because H5 file is kind of popular in Bioconductor, so we already have this HDF5 array package to read the vector in the H5 file. And also this one is the H5 data set is the function defined in Highfive package to read the data as an ALTREP. Now let's first check the values in the matrix. So not surprising, all the values are the same. But the A1, which is the HDF5 array, and you can see it's a special class of delayed matrix. And A2 is just a naive integer matrix. So you can confirm that by using the class function. And A1 is just it's a HDF5 matrix, and A2 is just a matrix. And so let's do some operations on the matrix. So let's first do the sum function in base R. And you see they gave us the same result, and that's good. And but actually, even though it looks the same, but actually the sum function for A1 is an S4 generic, and actually its definition is in the HDF5 array package, so that it implements the sum function so that its HDF5 matrix works like a regular matrix. But for A2, there's nothing special need to do for the sum. And the sum is just a function from base R. And as long as you define the ALTREP, every function from base R works for the ALTREP. So with the travel package, all the existing old functions are available out of box. And then let's try our silly sum function. So remember that mySum3 is the function to use the data pointer API to loop over the vector, and which is not surprising. So because it's designed for the vector, so you cannot you can see the arrows here. And but for the A2, it just works, and it gives you the expected result. So like I said, so all the existing code works without any change. All the things you need to do is to define your ALTREP object. And for the data frame, so because the HDF5 array only supports the matrix, supports the vector type, so I will just show how it works in the Highfive package. So it's the same function and with the data frame, and it reads as a df variable, and you see the type is data frame, and its value is just a normal data frame. And because there's no alter list features in R, so actually the data frame is the ALTREP data frame is implemented by making each column an ALTREP vector, and also the same column mean function, all the other functions works for the data frame. So that's what I would like to introduce in this talk. And here's my acknowledgements. So first, I would like to thank Martin Morgan, and he's my supervisor in the Bioconductor, and he bring me the idea of the ALTREP, and I learned a lot from him. So without his patience and help, and there's no chance for me to reach such level in ALTREP. So I would like special thanks for Martin Morgan. And also, I would like to thank Luke, Gabriel, and many other zealous programmers in RD mailing list. And I kept chattering in mailing list, asking about sometimes silly question about ALTREP. And but I always can get many useful response from these guys. I cannot list all of your names here, but I would like to say thank you to all of you guys. And also, I would like to thank Max Smith for the invitation. And also, thanks for BioC Forum for joining my talk. And I'm grateful to have a chance to show my works here. And so I will stop my talk and answer questions.
Thanks a lot, Jiefei. That was awesome. Really, really nice talk. I told you 40 minutes, and I think that was dead on, so that was perfect. So I'm sure people have questions, so I'm just going to open this up, and we seem to manage this without too much moderation normally, so let's turn on your mic, ask a question, and we'll see how it works.
Yeah, if I may, this was breathtakingly stunning. I mean, really, really well laid out, Jiefei. This was the clearest that I've seen in a talk in quite some time. I mean, truly impressive. So chapeau. Love to work some more on that. Two quick questions. And, I share the general sentiment. I mean, I'm fascinated by ALTREP, and I've looked at it multiple times, and I'm hand-waving to Luke, who I think is listening in, but I've also been a little, or more than a little, overwhelmed by the complexity. But when I see the region macro, I immediately think, isn't this meant to be passing in parallel? So should your performance nodes have a footnote, because conceptually, at least, this could work on several chunks at once, at least, for read-only access like reads. We're doing something similar in RSPB parallel. That was sort of the one. And the other is, of course, do you see a way to flag and warn use of read_ELT? Because it was, of course, such a performance killer for your otherwise very compelling alternative. Any way to intercept that? So that was two questions.
Okay. So your question is about us internal, right? Us interface.
Not really. That stuff I'm mostly familiar with, but you had a 3-panel, basically when you're comparing your 3 approach. Yeah, exactly. Get region to me to have an implicit promise of doing multiple regions at once. I haven't seen it used that way, but is that intended or possible? And if that's the case, then your GitHub 2 stars for this one may need a footnote, because if you actually drive this in parallel on many cores, it will be faster than even travel single-threaded.
Yeah. So actually, so I'm not in our core team, so I cannot speak for them. But I think you are right. Like there's a possibility to parallel this get region function, and maybe get a better performance out of it. And actually, I used to ask a question in the deep mailing list. So like I said, I keep chatting in the mailing list. So about like whether some R internals API RC interface is thread safe or not. So actually, like Luke tell me that at the current stage that it's better to assume that none of them are thread safe. So that the idea of parallelization is kind of risky right now. So you may avoid the assumption of some locality assumption of your variable. So I don't know if Luke has any word for it to say.
I mean, my gut feeling is that parallelization is kind of orthogonal to this. You can do it. I mean, because of the slowness with real ELT, you'd want to do something else first, but the others could be done in parallel, and I think they're mostly independent from my judgment, at least. One of the things with a summary, of course, you always have to worry about doing things in parallel is you're changing the numerical result. But in other things, of course, if you're not doing a summary, it's certainly viable.
Quick comment there. I guess you have to be careful about like when you have disk access and things like that. So it has to be optional.
Yeah, but it's very, very close to the canonical examples of Intel TBV or Data One or whatever they call it these days, which got carried over into RSPP parallel with workers and clients, because basically functions are defined to work on chunks, and then TBV is very nice in dealing with heuristics for giving us chunk size and whatever, that you don't have to worry about it, which we would have to do here, but otherwise it's very very close as a mental model, because certain things can work parallel, and as Luke says, in chunks more efficiently than on individual accesses, and maybe one day. But yeah, all those caveats about when or when not to access to our data structures, I mean, that's also all over the RCPP parallel package, because that's the first errors that we get, that people do that on SEXP types and that you cannot do because things may happen in parallel. So there it's always at the cost of initial copy over to a C++ data structure that then gets chunked. So I know about those vagaries too. I just hadn't seen that notion expressed where the region was meant to potentially go there. But yeah, it's a thought or not. Maybe one day.
Yeah. So before I go to your second question, I just want to add one more point here. So if your data is able to read in parallel, so like in this diagram, as in this program diagram show, and if you are able to load in parallel, and you could implement it in the travel package, and actually the operating system is able to load your data in parallel. R does not do that, but operating system does it. So that by accessing a pointer, actually the operating system will predict like what's your next behavior. So if it says that you are looping over a vector, then it will preload multiple chunks before you actually access it. So that's one possibility to bypass the limitation of the RC interface.
Can I ask you one quick question? The pointers you return that data PTR returns are writable. That's always been an unfortunate limitation, which is why I added the _RO for read-only ones. Because, for example, if you assume anything is inside of is sorted, for example, as soon as you return a writable pointer, all bets are off. What happens if somebody writes into a pointer that's gone through your framework? Does that do anything other than segfault?
That's a good question. Actually, if you want, here is the full set of API provided by the travel package. And you can see here is a lovely set region function in the travel package. Actually, not only it can read the data from the pointer, it can also set the data in the pointer. So every time you write the data back to a pointer, and this set region function can be called, so you will get notified that something is changed. So if you want to be, if someone writes data that break your saltiness assumption, so you can just define this set region function and just clear the saltiness flag. So just say maybe unknown saltiness or the other things.
Okay, sounds good. Thanks.
Jiefei, great talk. So yeah, I've also played around with ALTREP a bit, especially for sort of handling these large data sets. And in practical applications, one thing I immediately ran into was when I tried to do anything like so, the analysis would work well, it would work well all in memory. I could pretend I had like a 400 terabyte object in memory, and that was all good. But then as soon as I did something like, for example, save RDS, I think, the entire thing gets pulled into memory right, to then serialize it into the file. So I wonder if you have some thoughts on the sort of use cases, especially for HDF5, for example, especially on the use cases of, when you would want to have, when you would expose to the user these things that look like matrices but are actually ALTREPs, right?
Yes, I think that's a good question. And actually, so give me a second. So what you're asking question about the Highfive package. So actually, so I designed the travel package just for solving the challenges in the ALTREP features in R. So actually, I do not have an immediate answer for your question. So whether user want why do user want an ALTREP or not? And so I probably I think the one major reason is that it is easier for the developer to just work on the ALTREP, because if you load the data in R, to make it compatible with all the other code, you have to define your own version of that function. Like if you want it, your data structure works with some function, you have to define the some function. And what about the variance and the covariance, or even the mean function, or some maybe ggplot, or some other functions? That they all assume that your data has at least they can assume your data is a vector, and so by doing the ALTREP stuff, this make our life easier, because we won't need to worry about whether our object is compatible with the other function. So we don't have to define this. We don't have to reinvent the wheels.
I kind of thought that the save RDS problem that Aaron mentioned was probably because save RDS tries to realize the full vector, and then you have to allocate that memory. And in principle, the travel package would solve that problem, because the realization, it wouldn't realize the full data. But then in practice, almost certainly, this has been our experience, right, Jiefei? As soon as we start to go down one of those cases, you find some other problem that needs to be addressed at one level or another.
Yeah, it would definitely be really interesting to see how this could work with HDF5 matrix, for example. So when HDF5 matrix does its block processing to realize chunks, instead of creating a full matrix right away, you could create an ALTREP. And then whatever downstream functions need to work on that might be able to do so more efficiently, because they're not realizing the entire chunk. I don't know. There might be some. I mean, from my use cases, the advantage of the HDF5 matrix is that I can serialize that, right? And that just if I serialize your ALTREPs, I'll need to hold the path back to the that needs to hold the path back to the file, right?
I'm not quite sure how the save RDS works, but actually, if all you need is the serialization, then actually you can define the serialize function in the travel package.
Right.
So I have a comment and question, but first I want to second what others said. This was a brilliant work, brilliant presentation, beautiful. So I have tons of questions, but since we just talked about you can apply the sum function in base R now automatically without having to dispatch on class. This is more like an open question. It's do you think? I mean, do we now need a way to declare that these functions we implement actually support sum and mean, and what does it mean to do sum on an HDF file? And for instance, is that well defined now all of a sudden, or are we in an ambiguous space? Do we need a way to declare that these objects now support some, for instance? Because now you can call. Yeah, exactly.
Oh, there's no special action you need to do. So it just support, like because it will behave exactly the same as a regular vector.
So, but yeah, so I understood that, but that's like in your definition of the H5 data set, that's like in the documentation you're saying this object behaves like this. We had that, like, I think in Bioconductor we have said like matrix-like objects, there was like a little bit of a ambiguous world. I just wonder, do you think we're getting into such ambiguous world here too if we open up this possibility?
Yeah,
will people like start adding class objects saying I support this and this, or
I don't know.
I mean, you're basically saying okay, continue.
Yeah, I mean, maybe as a package developer who uses the travel package, like they can declare like what functions they support or they intend to support. But for the travel package, it's just a tool for creating the ALTREP object. So I'm not sure if that should be a job on the travel package to do such thing.
I mean,
yep.
Sorry, if I may, it seems like the biggest problem there is not whether or not something's supported, but whether it's supported efficiently, right? Because, all of these functions, if they see a matrix, they'll just, if you have a function that sees like a normal vector, it probably does like it just does a real, like converts it into a sort of full in-memory vector, right? And then just operates on that. Probably what a lot of these packages do if they're seeing an ALTREP. And then, I mean, whatever function it is, it'll probably work, but it'll, chew up all the memory on your machine while doing so. So yeah, an interesting question would be, what happens if it doesn't sort of natively handle the ALTREP status of the object that's being passed in, and then is it going to fail gracefully or just brick your computer, right?
Yeah, I can imagine like users will use these objects in a way you didn't anticipate. They call functions that you didn't think of. Yeah, but it's more like what will happen next in the R space when. A clarification question: where is the name travel coming from?
Okay, so the travel come from. So that's a really good question. The travel actually comes from this diagram. Like you start from the R word, and you go deep to the operating system, and then you go back to your user-defined function. So this is a really long trip. So that's why I call it travel.
Okay. Yep. And about that operating, is that a limit on modern operating systems, or could you go back like 15 years and get this to compile and work?
I'm not sure, because like this is a really simplified diagram. Actually, the travel is not directly attached to the operating system. Actually, there's another layer. So like Wheeler said, like everything can be solved by another level of indirection. So actually, and we cannot just hijack the pointer access request. So actually, we use the technique like called file mapping. So some of you may be very familiar with that topic. And our travel package is actually a file system in your operating system. So it creates a virtual file, and then map it into your memory. And so that's why it behaves like a pointer. But actually, when you access that file, and it will the request will be passed to our user-defined function. And if you ask me the compatibility, I will say like as long as actually travel use Docan library on Windows and Fuse library on Linux. So as long as the Fuse library supported it, so I think it should work.
I'll mention that Jiefei is a basketball player. He's always showing up with injuries and twisted backs and so on. So I thought of travel as something that you did in basketball, where you took the ball and ran to a different place where you weren't supposed to be. So.
Yeah, exactly. I borrowed the travel idea from the basketball, but actually, you see, that's clearly a long trip for a pointer to get the right data for you.
Basketball's not my sport, but don't we get penalized for traveling? I'm not sure we want to encourage that, right? Like this should work seamlessly, right?
Yeah, I mean, yeah, you get a certain penalty, like that may bring our first guy's question, like the element function. Okay, that's my performance comparison. Yes, our element function, we have a great performance penalty for the element one. And for the data pointer one, if you are able to allocate such large object in your machine, and you will see that the loop over a real pointer in your computer is really fast. It's way less than 15 seconds. So maybe if you want me guess, I will say 5 seconds for a real pointer. So that there's definitely some penalty for this kind of travel. But the good thing is that other than that, you have no way to support such large vector. So I mean, there's a trade-off between like your memory usage and your run speed. So you have to make the choice between them.
I have another question, which is more like me being a rookie with ALTREP. So is ALTREP mostly meant for read-only, or is there writing and updating too?
Oh, that's a good question. I would also like to ask Luke. Maybe if you don't ask this question, I may ask it a few months later in the mailing list. So actually, there is a set element function in RC interface. But what it actually does is just calling you data pointer to do its job, if I am not wrong. So which means that if your data is not in memory and with the traditional without the travel package, there's no way for you to set the element for an ALTREP. And I think like when I cannot speak for them, but that's my guess. Like when ALTREP is developed, like it is designed for the read-only object, like the attribute wrapper and the compact sequence. Such thing it's just read-only. There's no need to change anything in the ALTREP. Then maybe Luke can provide some insight in it.
Yeah, the prime motivation is read only, and I think my thinking was that we'll see at some point what we can do with allowing writing. The one object of the standard built-in ones that supports it is strings, so you can modify. When you have a deferred string, then you can change elements of that. We haven't added that to a lot of the others because there are some keeping things so that you maintain the pass by value semantics of R is tricky. And I know I had some thoughts that maybe this could be done, and I ended up, no, these are a whole bunch of reasons why this doesn't work. So at this point, it may, I'm fairly sure we can do more than we do now in terms of writable stuff, but it has to be approached pretty carefully because things you try and that if you do something off the cuff, it's going to end up somewhere producing results you don't like. So maybe we'll move to more writable stuff, but it needs thinking through.
And the travel-made ALTREP is actually designed for both read and write, so that even if you do not provide the set region function in the operation struct, and it's still writable. You can still write the data back to the pointer, and there's a built-in layer in the travel package to collect the data you read and also apply it like a mask to your original vector, so that your original vector is intact, but when you write it back, you are able to write it, and also you are able to read the data that you just read into.
Right. There's in the ALTREP examples organization on GitHub, there's a package called Mutable or something like that, which when I started out as this is how you do it, and it ended up with this is why all sorts of things don't work. So if you haven't looked at, I've now forgotten what the issues are, but if you haven't looked at that, I'd take a quick look and make sure if there are any issues mentioned there that might impact allowing your objects to be writable. Hopefully the answer is no, but if you haven't looked, I encourage you to take a quick look.
Okay, thanks. Yeah, I know that package. Yeah, that's also my introduction package for the ALTREP. That I learned a lot from its code.
If there are no more questions, I'd like to thank Jiefei again. That was a really awesome talk, as has been said several times by many people here. Like, that was really very impressive, really cool work. Yeah, next week is the European Bioconductor Conference. It's on East Coast time, I think. So it might be okay for some of you to attend as well. Hopefully I'll see lots of you there. And the next session for this call will be third week of January. I think at the moment we have penciled in some people from Microsoft's genomics team, but I need to confirm that with Nitesh. He's still on the call. We need to talk about that, Nitesh. So thank you very much again for attending, and see you guys next week and next month.
Thank you. See you guys.